Brandon, don't know what the hardest stuff was, or the whole thing was confusing? Getting started, how everything was set up. Yeah. Like I said yesterday, it is somewhat deliberately a little bit of a shambles. But again, on purpose, for practice, working in conditions like those, I've certainly been in much worse where the documentation was just all wrong. Stuff was missing all over the place. And it just happens. It's just the way it is. For business reasons, lots of the time, nobody's been paid to spend the time to do enough work to prepare the project, and then you become the one who gets paid to do enough work to prepare the project. And that actually works out for the best in many ways because you're the expert on how these things get built out. And so people rely on you to make decisions about what the best plan of attack is and to ask questions to clarify what needs to be known. Because other people who are making up the idea might not even realize that there could be a potential problem there. They need the domain expert, you, to figure it out. About how long did it take you all to how long did you spend on the reading stuff part before doing any of the coding part? Hour reading, hour coding, 30, 45 minutes? All right. It's really hard to spend too much time in the understanding and planning phase of a project. The only real pressure you have at work is that your boss wants something to get done and the company wants to stop paying you to do the problem as soon as they can so they can have a better bottom line. That's really it. But when I'm working on stuff on my own, I will spend sometimes ages thinking about a problem before I start coding on it. And every second I spend thinking about it, that takes time off how long it takes me to actually write once I've got it figured out. Hours of debugging can save you minutes of planning, right? Any other observations? Some people say that this was the hardest won battle to get the number 8 to print on the screen that they've ever done. Or questions about this. This is the Q&A part. All I'm doing is asking questions, but if you all have questions. It is. So what's really amazing about how complicated this thing is, it's back in the 80s, like the home computer revolution, they build these computers, they build CPUs, they build them out of transistors now and then. But the number of transistors, which you can think of as like little tiny switches, the number of transistors on a CPU, a home computer back in the 80s, was like 6,000, 7,000. So that kind of gives you an idea of the complexity of the machine. So it's got like 6,000 or 7,000 tiny switches inside this CPU. But a modern CPU has more like 20 billion transistors in it. It's utter insanity how amazingly complicated modern CPUs are. And back in the 80s, there was this time when you could study hard and get like a pretty good 90% level idea of how a computer worked from the ground up, like from the physics level all the way up through how it was displaying stuff on the screen. The machines were actually relatively simple. But now you got to have a PhD just to understand like cache coherency in a modern CPU, just that one little part of it. Aren't transistors thinner than rays of light? I don't know. How are we measuring the thinness of a ray of light? The wavelength? In that case, yes. It's all super thin. If you want to learn more about it, look up X-ray lithography on Wikipedia. But that's beyond the scope. But you can take a couple transistors, which, like I said, are little switches basically, and put them together, and you can form what we call a logic gate that performs a really basic operation. And some of these you're already familiar with in Boolean land with and or. But today we'll talk more about how this works with numbers. Let's see here. Oh, and on the transistor front, they're always on the lookout for ways to make transistors smaller. So can we get that switching behavior that a transistor has? Like how small can you make that? And way back in the day, like in the 40s, we had a couple options. Well, really when computers started, people were using vacuum tubes, which had the same switch behavior that a transistor has. But they're massive and they burn out and they're a royal pain. So they started replacing them with relays, which are a kind of electromechanical switch. And that had the same behavior. And finally, sometime in the 70s, I think Texas Instruments came up with like a solid state semiconductor transistor. And that was the revolution that happened at that point. But, we used to make them out of vacuum tubes. Now we make them out of semiconductors. But who's to say in the future we won't make them out of something else entirely? Like, is it possible to make a transistor that's just a few atoms big? And if so, we'll have another revolution of scale. So, oh yeah, at these scales, I can't even begin to imagine. Like, you have to take into account, just taking into account the time it takes for electricity to propagate down a tiny wire, like a microscopic wire inside the CPU. That has to be taken into consideration. And that's just like regular electric stuff. When you start getting weird stuff starts happening when you start doing things at these speeds, at these tiny scales. It's just awesome. All of you have taken pictures with your phones, I'm presuming. Uh, Phones use flash memory to store data. So every time you take a picture, it has to store all that data, right? Flash memory makes use of something called quantum electron tunneling, which is where an electron can spontaneously move from one side of a physical space to the other, like without being in the middle. It's like really spooky and weird, and yet we're using it to store data. It's amazing. Brandon, you probably know more about it than I do. So my knowledge basically stops at the software end. Daniel, I got the ALU to one line, all the ALU to one line, all the ALUs to one line except compare. Is there a simple bitwise or similar I can use to make it a one-liner? Probably, and I don't know what it is. Every time I've implemented compare, I've done it in 3 lines. So, but I'll bet there's something. Daniel, Google for Hacker's Delight and check out chapter 2 and see if there's, because that's free online. Check out chapter 2 of Hacker's Delight and see if there's something in there with bitwise stuff that might help for comparisons. If you do find a one-liner, it's going to be ugly, so be sure to comment it. Steve, I used to use this guy, this accountant, who he was. What did he tell me? It was when, this isn't political, but when Trump became president, Trump promised to like change the tax system, and my accountant is like, you know what? I'm just going to retire because I don't want to learn it. Like, he was kind of close to retirement, and he's like, I just hope that I can retire before the tax code changes so I don't have to learn that new stuff. And as awesome as quantum computing is, I kind of feel the same way, because unless there's a good compiler, I'm just going to be lost. Right now, quantum computing is like for physicists and stuff. And all these ideas about how I know to solve problems, I'm going to have to come up with completely new ideas for how to solve them. And it'll be giant. There just better be a good compiler, then I can keep doing it. But I haven't messed with Q#. Anyway, any other questions about the project stuff so far? Maybe if we have any time at the end, I'll geek out a little more on quantum computers and cryptography, but that's too far off topic for now. Yeah, Brandon, I don't even have AC at this house, so absolute zero is out of the question. All right. Let's hack on some Bitwise stuff here. And then after that, I'm going to take that Beej machine from yesterday, and I've got that program hard-coded in there, the same way in your LS8 you have the program hard-coded. And I'm going to pull that out, and I'm going to put it into different files so I can run different programs with my program on the command line. So we'll see how to do that today. And then I think for today, there's only one more instruction to be implemented, the multiply instruction. So we'll talk about that a little bit too. All right. Let's see here. Yes, I just keep not updating this. All right, Bitwise operations. So let me ask this question first. Have you all seen a truth table? I can't remember if this shows up earlier in the curriculum or not. Does that ring a bell? Or no? No, all right. No is enough. So the truth table, this is something that tells you when, for a particular set of inputs, the result is true for a certain operation. Let me explain what I'm saying. So I'm going to have two inputs, A and B, and these can either be true or false. And I'm going to have one output, which is A and B. Let's say. And you can think about this in a Boolean sense right now, just like the AND operator. If X equals 1 and Y equals 2, then we do something. So you can think of this in the Boolean sense for the moment. And so the truth table tells us for given inputs what the result is. And so here I'm listing all the different combinations of inputs that we can have. And we basically just look up the answer for a particular line. So if A is true and B is true, then the question is, what's this result right here? And one way you can ask yourself this question is, if I wrote some code that looked like this, oops, don't need parentheses in this language. I was writing C last night. I'm going to get C stuff in here. If A and B would this happen? So this is the question we want to answer right here. So if you wrote Python code that had this Boolean in it, so if A and B are both true, then the result of A and B is true, right? Because if they're both true, then yes, this would happen. But if either one of them is false, then this is not going to happen. Or if both of them are false, it's not going to happen. And so we look at the rest of these, one or both of them are false. So for all the rest of them, that's not going to happen. And this is our truth table right here for and. And so it's just a little helpful lookup table where we can take a look. It's like, oh, if A is false and B is true, then the result is false. Doesn't happen. Make sense? I mean, we haven't talked about how to use this yet, but we'll get there. What's everybody thinking? I want to have this stepping stone down before we move on. Could we do another column for C and have the same for A and B and C? Yeah, we absolutely could. Although in almost all my examples here, I'm just going to use 2 because it's a lot easier to write out. So if I've got 3, I now need every combination of this, which is true, false, true, true, false, false, and then the same thing again, except all these are false. So yeah, so we could ask ourselves, we could do a 3 input and, we call this, or add that to the end. And then we can ask ourselves the same question. If A and B and C, would this happen? And the answer is yes, it happens if all 3 of them are true. And so we've got one true right here where all 3 of them are true, but in all other cases, the thing is false. Yep. But for this, we'll just do 2 inputs. So let me ask this question then. I'm going to throw another truth table down here, and we're going to get rid of this, and we're going to try something else. So again, we're asking this question right here. If A or B, would this happen? So what's this column going to look like out here? Yeah, if either one of them is true, then we go for it. But if they're both false, then we don't. All right. Cool. There are 2 more tables I want to show you right here. This one just has 1 input, A and not A. And the way this works is it just inverts it. We call this an inverter. So if the input is true, then the output is false, and so on. And that works just like if you had some Python, this would be false, right? Okay. Let's do this last one, and then we're going to switch everything over to numbers. How many of you have heard of XOR? Yeah. This works just like regular OR, except it's only true if one of them as true. One of them must be exclusively true. They can't both be true. So if they're both true, the result is false. But if both are false, the result is false. But if one of them is exclusively true, then we have that. Now, there's no XOR operator in Boolean logic. We've got and or and not that we can use with our if statements, but we don't have an XOR. But when we get into the land of Bitwise, we do have an XOR. I'm going to get rid of this table and scooch it way to the bottom so it's not in the way, because the 3 inputs is huge. Let's see. Let's also move our inverter up to here. Okay. So we're used to doing this with Boolean stuff, with trues and falses. But remember, I said yesterday, the computer doesn't have any concept of true and false. What's the only thing the computer can store and manipulate? Voltage. Well, yes, that's deeper than I was thinking, but that's true. But it uses voltage to represent ones and zeros, numbers. That's all it's got. It doesn't have true and false. It's just got ones and zeros. So coming full circle to what we talked about yesterday with binary, one of the beautiful things about binary for computing is that 1 and 0 maps really well to true and false. And if you think about it, virtually all the software we write depends on having Boolean logic in it. We've got conditions all over the place. When was the last time you wrote a program that didn't have an if statement in it? So this beautiful mapping of true and false to ones and zeros takes us from the land of these true and false concepts to the land of numbers, which is where the CPU works. Whoops, what did I just mess up with my regex? That was about to be a beautiful substitution. True with 1, there we go. And replace false with 0. So exact same truth tables. We've just got 1 for true and false, or 0 for false now. Now we're in the land where the computer can do things. And we call these kinds of operations the bitwise operations when we start operating on numbers instead of on true and false. True and false is a language construct that exists in Python. And Python can do Boolean stuff with true and false, like we've been doing the whole time. But it can also do bitwise stuff with numbers. Before I go on, how are we all feeling with this idea? We still all on board, or questions or comments? Try to think of a use case. Yeah, we'll get there. Let me give you a little spoiler though for the use case. Using bitwise stuff enables us to manipulate individual bits within a number. So within a Boolean number, we're able to set or clear individual bits. We're able to extract bits out of the number. We're even able to, as we'll see in a bit, be able to shift the bits in the number left or right. And so if certain bits inside a number have meaning, we can extract those bits and look for that meaning. One of the simplest use cases you might think of is you might have a 32-bit number, and each of those digits represents a a Boolean value, true or false. So inside one number, you could have 32 Booleans just in one number. And that's pretty compact. This can come into play like, hey, do I have to send 1,000,000 true false values out over the network? Sure, JSON's great, but true and false in JSON is gigantic. If I could pack those all into numbers and then write them down in hexadecimal inside the JSON, suddenly the amount of data transmission drops by a factor of, I don't know, like orders of magnitude. So yep. All right. So let's run with this a little bit more. What are these bitwise operations? What are they, or operators, like I should say, what do they look like in Python? So in Python, for Booleans, we're used to and or, and not. Maybe I can write this as a better table here. I'm just going to write and then we'll make a Boolean column out here so that we see what it is. Or, and not, and XOR. So these are all our operations we want to do, and they do have Boolean equivalents, some of them, like and or, not. But they also have bitwise versions. This is Python here. But these bitwise operators were stolen from C, I think. A lot of languages use the exact same ones. So the bitwise operation for and, remember, Boolean works on true, false. Bitwise works on numbers. Bitwise operator is this. The bitwise operator for or is a pipe. For not is a tilde. And then XOR, which doesn't have anything in Boolean, is a caret. No, is that right? It is, right? Yes. Like, that's not exponentiation. We'll find out in a second if it's right or not. Bring up Python REPL and mess with this a little bit. Exponentiation is 2 asterisks, yeah. So the Boolean stuff works as we expect. True and false is false. Great. But let's do some numbers with some bitwise stuff. So we should be able to do the same thing. True and false is false. True and true is true. Let's try one exclusive or one. So this should be 0 because with exclusive or, only one of them can be true. But if one of them is true, then the result is true. Or if the other one is true, whoops, I don't know where those numbers came from, then it's true. And if they're both false, then it's false. So we can do this with numbers. Great. Seems the same. Why would we bother? We bother because we can actually do other things like this. Man, there's some hotkey expressed. I just threw in 2 random numbers there and XOR'd them together. Those are way more than 1 bit each. Let's see if we can figure out how that works. I'm going to use and. So remember, and is true if both. Oh, it's when I hit shift space. Shift space puts in that weird thing. With and, if both of them are true, the result is true. But if either is false, the result is false. So let's see if we can figure out how this works. I'm going to write a couple 2-bit binary numbers here, like 1, 1. And then we're going to and it with 0, 1. These are binary numbers. The 0B in front means it's binary. So we're doing a bitwise and between these 2 numbers. What's the answer going to be, do you think? Well, it's going to be numeric. So it won't be the value true because that's a Boolean value, but it's going to be a numeric value. It'll be 1 or 0, 1. Put a leading 0 on it. And usually when programmers are writing down binary numbers, if they think about how many bits are in the number, and they tend to put leading zeros out on the front, even if those are all, even the leading zeros don't matter, but why? How would we get 0, 1 or 1 out of this? It's 3 on 1. So 1 and 1 is 1. And 1 and 0 is 0. Sure enough, the answer is 1. And yeah, we did that. The way we did that was a column at a time. So 1, 1 and 0, 1, we just did individual columns. So took this column, added those together. 1 and 1, that's 1. Then we took this column, added those together. 1 and 0, that's 0. That's your answer. So yeah. So we can use these bitwise operations on multi-bit numbers. It'll do all the bits at once. Kind of cool. Let's see. No way to represent XOR with Booleans. Looks like Jack has the answer there. The letter B is indicating that's a binary number. So remember yesterday, I said when you write down a number, you have to say what the base is. And if you don't put a base on it, the computer assumes you mean base 10. But these two numbers, 1, 1 and 0, 1, these are binary numbers. They're base 2. And I had to specify that they're base 2 by putting 0B in front of them. It's a good question. Does that make sense? Because if I didn't put a 0B in front of it, it would just be the number 11 in decimal. So we're just checking 3 and 1. Yep. Yeah, so if I ask Python, what's the value of this in decimal? It's going to tell me 3. Because binary 1, 1 is 3 in decimal. It's 1 plus 2. So the 0B is just me telling Python what base that number is. I wrote it down. I had to specify the base. So when I think about these things, I don't actually think about them in decimal because my brain doesn't convert between decimal and binary very well. So I tend to think about them in binary when I'm doing bitwise. If 0B is base 2, the B stands for binary. What is base 7? There is no way to specify base 7 easily with a constant in Python. You can do it, but you have to do it in a string, I think. So here's a base 7 number. I could say, please convert that to a numeric value in base 7, and it'll do it for me. But I don't know of any, there's no prefix like 0B for base 7. Those are good questions. I love it. Does that answer that, Jack? All we've got is 0B for base 2, 0X for base 16, and I think 0O for base 8. Yeah. 0O for base 8 if you want. O stands for octal. Barely anybody uses base 8, so we don't even talk about it. Let's see. So what does 3 and 1 mean in decimal? Like bitwise 3 and 1? We can just, the way you would get that answer is you could just do the conversion here. If you know that all these guys are binary, we could just convert these binaries into decimal numbers. So this is decimal 3, this is decimal 1, the result is decimal 1. Remember, the base only matters when we write the number down. When it's doing some calculation, like a bitwise and, it's doing this on a pure numeric sense. Although deep down, of course, it's doing binary. But from our perspective as programmers, we can just forget about the base and let's see. So does it make sense to think of it in decimal? Oh, if you say 3 and 1, oh yeah, I see what you're saying. Because in everyday speech between people who aren't computer people, and means plus, but this is a different and. So this is bitwise and, completely different than plus. Yep. It's the old smart ass computer scientist joke. When you go out for dinner and they say, "Would you like soup or salad?" You say yes. uh, okay, so let's see if we can make some use of this crazy thing. We haven't talked about shift yet, but let's do that. Let's see, what time is it? Quarter till, plenty of time. So I'm going to talk about bit shifting. This means taking the bits of a number, I'm going to write these in binary here, and moving them left or right. So we could take this number and we could shift it to the right, which would mean basically doing this. But when we do that, a couple things happen. One, the number that was over here that got shifted off here, it falls off the end into nothingness. So it's gone. And then we get a leading 0 up here. So we could shift it right again. Same thing happens. This bit shifts off the end, falls away into oblivion, into the bit bucket, if you will. And then a leading 0 gets put on the front. And you can keep shifting the number this way. And you can also go the other direction, of course. And it depends on how big the number is or how many bits the number can be. This depends on the language. Python doesn't actually have an upper end to it. But we can shift this direction, and a 0 gets put in here. And if there's still room in the number for this 1, it just keeps getting pushed out. If you run out of bits in the number, like in the C programming language, there's a fixed number of bits that exist. It will fall off the end if it gets pushed too high. But in Python, I think they just grow forever. Let's do a quick test. I'm going to take the number 1, and I'm going to left shift it by 1,000,000. Yeah, so Python doesn't have an upper limit on that, apparently. Brandon, you're absolutely right. On real computers, there's a flag that holds the value, like the carry flag or the overflow flag or something will hold the values that bit shift off the end, but the LS8 doesn't have any such flag. Sean, let's see, so in a low-level language, do you have to garbage collect the dropped bits? What happens to those things? So no, you don't. And it's kind of neat because it's all about how the machine is constructed, right? It's a bunch of wires with voltages. And so if you think of, let me see if I can draw this picture. if you think of the simplest version of this, forgetting about the flag that it goes into, uh, let's see here. Let's say I have a number here. It's going to be awesome art. I'm drawing with my mouse. 4, 5, 6, 7. So here's an 8-bit number. So each of these slots can have like ones and zeros in them, and so on, right? So 8-bit number in here, and I want to shift this right by 1, and that's our. So that number's our input. Woo! And this is our output. 1, 2, 3, 4, 5, 6, 7. So in the land of physical construction, one way to shift this to the right would be to take a wire that had this voltage on it and take that wire and just put it over here. And then I could take this wire and put it over here, and so on. So for each of these input bits, I've got physical wires that are shifting them over to the output. And then, did I miscount? I have the wrong number of bits somewhere. I don't know. Let's just do that. All right. So they all get shifted. Oh wait, no, one gets shifted off the end. Sorry. Undo. That's why I didn't have the right number of bits. So that one goes there. This one goes off into oblivion, like to a ground or something, like an electric drain. And then this one right here just gets a like low voltage 0 coming into it all the time. So in hardware, and here I'm really hand waving a lot. I don't know how they actually do this in hardware, but this is one way you could think about it. Like they have actual physical wire. So does it have to be garbage collected? No, because it's just a voltage, right? It's just a voltage that you send off into nothingness. At this low level, it's all physics and electricity and stuff. Pretty crazy. So is it a one-to-one with the hardware? Yeah. I'm reluctant to say much because, like I said, I don't really know what I'm talking about with hardware. But yeah. Yep. Yeah. So if the LS8 existed, since the LS8 is a 8-bit machine, uh, we might have something like this on the LS8. So if this is my ALU for doing math, ALU, that's an L, I swear. Okay, I surrender. ALU. We might have a couple inputs because the ALU does things like add and subtract, right? But it does that on registers, and each of those registers is 8 bits big. So coming in here, 3, 4, 5, 6, 7, 8. We're gonna have 8 wires to represent like one of the registers that gets used. And then we might have 8 more down here. I'm gonna take a little shortcut. I'm just gonna say this is 8 wires right here, so I don't have to draw them all. And then we have another register. So maybe register A and register B. And we just have actual physical wires, 1 wire per bit, representing those 2 registers that are coming in. And then we'll probably have another couple wires in here that tell us what the operation is. Like, is it plus or minus or whatever? And then the ALU will do the work and give us some output. So yeah, every one of those individual ones and zeros maps to a voltage on a wire inside the machine. Pretty nuts. And thankfully, the LS8 is an 8-bit machine, so I only had to draw 8 wires here. Unlike your x86-64, which is a 64-bit machine, it's got 64 wires running all over the place. Wish we had more time to talk about this because I taught a computer architecture course at Oregon State as an adjunct, and we actually built like a simple computer. We built it out with logic diagrams. It couldn't really do much, but it could do some math on registers, and it was a pretty neat little thing to be able to see like the program counter being stored there, how the information got fed in from the individual instructions into the ALU to get the math done, stuff like that. Sorry, Brandon, x86 or ARM in reference to what? Yeah, it's pretty nuts. Like the actual bit layouts of these instructions are really deliberate because the bit layouts of the instructions represent the voltages that have to go do things at different parts of the CPU. So they're not just numbers they chose randomly. For the instructions themselves, they're laid out very deliberately. Think about it like, I'll see if I can find a picture of this on break, but there are looms that make cloth and they make patterns on the cloth, and you can automate them by putting in like punch cards that describe the pattern that comes out of the cloth. And it's very similar to how instructions are laid out, and the instructions get fed into different parts of the CPU. And neat stuff. All right, let's use this bit shifting stuff and what we've learned about Bitwise to get some cool information out of the LS8. Cool. So on the LS8, in the spec, oops, I'm still drawing. Clear all my drawings, stop drawing stuff. Let's see here. There's instructions, LS8 spec. Let's just see if I can keep one of these open permanent like. If you were skimming the spec, you may have noticed this section right here, the instruction layout. And this tells us the meanings of the bits in the first byte of each instruction. They're labeled here, A, B, C, and D. Now, one thing that you may or may not find useful, I encourage you to implement this because it's kind of a neat way of doing things, is this thing, the number of operands in the opcode. Remember, operands are arguments. The opcode is the instruction, operands are the arguments to the instruction. This tells us how many operands are in for this opcode, these first 2 bits. So AA is going to be a 2-bit number, which means it can go from 0 to 3. It can be 00, 01, 10, or 11. None of the operands, or none of the opcodes have 3 operands, but some have 2. So we need 2 bits to represent that. Now, let me ask this question. If you know how many operands the opcode has, does that buy you anything in how you've coded up your LS8? It does, but what is it? Tells you how far to advance the PC. So in that Beej machine from yesterday, I've got this stuff hard-coded all over the place. Oh, hey, if this was a 3-byte instruction, let's move the PC ahead by 3. If it's 2 bytes, let's move it ahead by 2. And you might have something similar to that. But wouldn't it be neat if we could just say PC, at the end of all this, instead of doing it for all of those, I could just say PC plus equals the instruction length. If I could just compute that somehow, then I could just add on that onto the PC, and I wouldn't have to have all these things all over the place hard-coded in there. And this is actually much closer to how a real CPU would work. So if I could compute this, the instruction length, then I could just add that on. I wouldn't have to hard code all these individual ones. Now I can't do that with my machine with the Beej machine because my instructions don't have any special meaning in their values. They're just 1, 2, 3, and 4. But in the LS8, these first 2 bits of the opcode do have meaning. They tell you how many operands there are. And we can use that number to figure out how long the instruction is. So let's check this out. The first 2 bits of the opcode tell us how many operands there are. Let's make sure this is the case. So with add, we can use add. Add takes 2 operands, 2 arguments. So the value in the first 2 bits of the opcode should be 2. And if we look at it right here, it is 1 0 binary is 2 in decimal. This is telling us that add takes 2 arguments, register A and register B. Great. Another one, and. Looks like it takes 2 arguments, register A and register B. Sure enough, first 2 bits, the value is 2. Call only takes 1 argument, the register. And if we look at the first 2 bits, the value is 1, telling us there is just 1 argument. There is just 1 operand. And somewhere in here, we've got some that don't do any. Halt. It has no arguments. Sure enough, the first 2 bits are 0, telling us there are none. So if we could get that value out of there, those first 2 bits out of there, all we have to do is add 1 to it to tell us how big the instruction is. Because the first 2 bits tell us how many operands, and then we add 1 for the opcode. And that tells us that this is, for example, a 3-byte instruction. So given what we know, how do we get those 2 bits out of there? Right now, this number is a big old number, 101000011. I just want the 10 part. That's all I want. So let's take the example, the div instruction for divide, and so the div instruction is this. And so we've got that to start. And what I want to do is some kind of transformation that turns this into this number. I want these 2 bits right here to end up down here. Yeah, that's a right shift by 6 bits. If we take this thing and I right shift it once and again, 3, 4, come on you, 5, and 6. And remember, all these bits over here fall off the end as we shift them away. Do I have this highlighted right? Yeah, so all these bits out here, those fall off the end into space. And then leading zeros don't mean anything mathematically, but we often put them in. And so if we right shift this guy by 6, 1, 2, 3, 4, 5, 6, then we end up with the answer that we're looking for. Great. So on the LS8, that magical code to get the length of the instruction is the instruction value, right shifted by 6. This is the right shift operator right here. Sorry, that's not the instruction length total. Let me write this another way. Operand count is really what it is. And then the instruction length is the operand count plus 1. And that's plus 1 to count the opcode. The opcode being the instruction itself. And now we can do this. So we can save ourselves some hassle by just having it compute the length of the instruction and use that to figure out how far to move the PC next time. Well, so kind of. To get the instruction value left shift by the operand count, that would get you a number, but it's not the complete instruction. So if I took my operand count, 4, 5, 6, 7, 8, which is this, the operand count is 2, and I started left shifting it, then we'd end up with something like this. Oops, was that too many? Yes. But of course, it just gets filled with zeros at the end. So yes, if we left shifted it by 6, the operand count would end up back up here where it belongs. But the rest of the number here has been nuked. So it's almost like if we shifted it all right, we pushed all that number, we pushed all the rest of the instruction bits off into oblivion, and then we shifted it back, but we didn't get those numbers back because they were just gone. So we ended up with part of the instruction. Turns out the rest of the bits have meaning-ish, and you could extract those in the same way. And later on, we probably, oops, I passed it. We probably do want to extract some of this stuff. Would I make a copy of the initial value and save it in a register? Yeah, I do. When I coded this up, I saved it in, well, here it's written down as instruction value, but technically it's called the instruction register inside the CPU. But this is not destructive. I want to be clear that this line right here is not destructive. And it may seem destructive at first, but it's not, because it's just doing this calculation as an intermediate calculation. Let me show you that it's something that is comparable to. So see how this is not destructive to A? A doesn't change, right? We just added 2 to it, but A itself doesn't change. It's exactly the same thing with this. The calculation is still done. A plus 2 is done. A right shifted 2 is done, but it doesn't affect A. If we wanted it to affect A, we'd have to do this. Or we could also do shortcut that. Those are equivalent lines. Why couldn't I shift left line 81 to get the instruction value? Well, wait, let me get some clarification here, because line 81 is the instruction value. To get the DDD part.
Like when you did it, it was destructive on line 84, right? Like when you bit shifted right.
Right.
And then you try to bit shift left with that operand count. That was destructive, right? But like, why couldn't you just bit shift left with line 81 instead? Just twice though, like just 2 times.
To get
the to get this guy here.
So I left shifted twice, and then to get what out of that?
The instruction itself, I guess. This is what I'm thinking of as like an instruction value, and this is the operand argument. length. You see me drawing on your screen?
Oh yeah, sorry. So yeah, that thing is the instruction itself. I guess I'm confused about what we're trying to extract out of it. Or
This part.
okay, okay. So just get those bits. That's all we want. Okay, I think this is this was the part that I was going to talk about next, but you can let me know if it's not.
Okay.
Let's see, 10:07. Let's thrash this out right before the break because I don't think it'll take too long. If you want to pull just some bits out of the number, if the bits are already on the right, we can actually do it without shifting. Let's say we want to get, so these, let's say we want to extract those numbers, or maybe just these, the ones at the bottom. We don't actually have to shift to make that happen. We can mask it. And we can do that with us by using a certain bitwise operator and a certain bit pattern to preserve these bits right here while changing all of these bits to 0. And that would give us that part of the number. So any ideas based on all the bitwise stuff we've done so far? Remember that example of bitwise 1-1 and 0-1 and what the result of that was? Yeah, we'll get to that question in just a second. So it turns out you can basically stencil numbers. You know, if you have like spray paint and a stencil, and you put the stencil up and you spray paint over it, where the stencil is, the spray paint doesn't come through. But where the stencil isn't, the spray paint does come through, and you end up with the result. You can stencil numbers out so that this part comes through and this part doesn't. And we can do that with something called an AND mask. And I'm just going to use bitwise AND to make that happen. And I'm going to put zeros where I don't want the number to come through. I'm going to put ones where I do want the number to come through. This is an AND mask. And because anything and 0 is 0, that means all these bits will get nuked in the result. These will all be 0. And then every place we have a 1 down here in the mask, these bits will be preserved. If they're 0, they'll stay 0. If they're 1, they'll stay 1. And so we see in this example, these bits got nuked. These bits got preserved. Whoa. Now, what if you wanted to get a middle bit out of here? Check this out. Bit C right here is 1 if this instruction sets the PC. We'll actually use that later. So let's see if we can extract it. So we want that bit out of there. I'm going to take this exact same number, and we want to get, which one? This one. We want to extract that 1 bit. We want to see if that is a 1 or a 0. So given what we know about AND masks and bit shifting, how can we get this 1 number out of there? We can AND it. We can put an AND mask on here, nuke everything but the number we're interested in. We're stenciling out the entire input except for this 1 number right here. And that's going to give us this result, 0, 0, well, it's all zeros. But this is the bit we're interested in right here. It has come through because that's the only hole in the stencil. And then we can shift it right by 4. And so if we take this number, we right shift it by 4, we end up, well, with 0 again. But what's important is that the bit we were interested in right here has now been shifted down to here on the right side of the number. And we have to do that shift. If that's confusing, think about it in base 10 for a second. Let's think about it in decimal. If I have a decimal number like 1, 2, 3, 4, 5, and I'm interested in that number, 23, I can't just do this because that's not 23, that's 2300. So I can mask it to get the 23, but then I have to right shift it to get the 23 down here, so the actual value is 23. So we just did the exact same thing with binary right here. And so for another instruction, where this might be a 1, where the instruction does set the PC, then that 1 would shine through the mask. Then we'd right shift it from here by 4, and we'd see the result down here. So using masks and shifting, we're able to extract individual bits or sets of bits from a number. Pretty nuts. In my practical experience, I shouldn't say this entirely, but the only place this would come into play in a modern scenario would be a case where you're trying to minimize the amount of data that is being sent. We kind of talked about this at the very beginning. Let's say you have 1,000,000 Booleans. There's a way to pack those 1,000,000 Booleans into numbers and represent them in a much smaller space than actually writing out true and false in a JSON file. So it can be an optimization that gets used. But largely, right now, we're talking about it so that you get practice solving problems. And also, it's good to know how the machine works at this deep level. Not that you're ever going to operate down there, but when you understand how the machine is doing its stuff and it becomes more demystified, and you're like, wait a second, underneath all this stuff, it's executing these simple instructions. That's all it's doing. It's like doing some math and it's moving the PC around. That's it. You get more familiar with the medium in which you're doing your work. And the more familiar you are, the more relaxed you are, the more just comfortable you are. And that makes your craft that much easier. So one of the reasons we talk about this stuff. If AND is for masking, what's OR and XOR used for? So OR is like the opposite. So with AND, you can clear bits, and with OR, you can set bits. So if you want to turn bits off, you AND them with a mask to get rid of them. If you want to turn bits on, set them from 0 to 1, you can OR them. So between AND, OR, and shift, you can turn on or off individual bits or sets of bits in any number. And XOR has 2 properties that get frequently used at this low level. One of them is if you XOR any number with itself, the result is 0. So you could clear a register by XORing it with itself, for example. And on old CPUs, that used to be faster than setting it to 0. So, but the other cool thing that you can do with XOR is if you XOR a number with another number, you'll get a result. And then if you XOR that result with the same XOR you used before, you'll get the original number. So you can XOR a number on and then XOR that same number off. Also, it tends to invert things. So if you have all ones, or if you have a pattern of 1s and 0s, you can XOR it with all 1s to invert it. So yeah, what Brandon said. That's Brandon, that's the swap, right? Yeah. Let's see, what was that other? Let me see if I can write it down right. So if we take a number, let's take some random numbers here, and let's XOR them together. So it's true, XOR is true if one of them is true, but not the other. So those are both true, so that's false, that's true, that's false, true. Tell me if I make a mistake. So I got this result, right? And is this gonna work right? If I XOR it with the same thing again, then let's see, 0 XOR 1 is 1, and 0, 1, 0, 1, 0, 1, 0. So check it out. I took this number, we'll call it A, and I XORed it with this number X, and we got a result. And then I took the result, and I XORed it with X again, and we got A out of it. Yeah, if you like this stuff, like I said, check out Hacker's Delight. Google that thing, and there is crazy, crazy stuff in there. Also, the computer is blazingly fast at these. It excels at manipulating ones and zeros. So these instructions all take place in a single clock cycle, which used to be a bigger deal back in the day when not so many instructions took place in a single clock cycle. But yeah, lots of cryptography also makes use of these things. All right, we're overdue for a break. Let's do a 10-minute break. And when we come back, we'll do some kind of simpler stuff today. We'll do some file I/O to unhard code my machine code in the Beej machine. And then that's about it. But definitely break time. Y'all been super sports on the Bitwise stuff. Let's see, what are we listening to today? Oh, 80s was next up. Dance 80s. All right, get you all in 10 minutes. Not the most awesome 80s dance mix. I know, right? Need the beat to drop there. All right. Okay, so I'll post all this Bitwise stuff to the Notepad channel, but I want to pop back into this computer for a little bit and unhard code this program right here. So I have this hard coded into memory, but what I really want to be able to do, save this in a file and then run that file. So this way I could have multiple different programs in different files, and I could use this program here to run them all. So I got to do a couple things to make that happen. I've got these written down as like print Beej and stuff, and these are numbers, right? Print Beej is 1. So I'm going to have to save these as numbers instead of like this. I'll have to save those in a different file. Let's just start with that. I'll call it program 1. And then I'm going to take these things and I'm going to put them over here. And I basically want to convert them to numbers and get rid of all those commas. I'll leave the comments in because like in the LS8 programs, there are comments in there. But I'll ignore those comments. So first things first, I'm going to get rid of all the commas. This isn't something that you have to do today. Oops, that's not what I wanted to substitute. This is something you have to do today because all those .ls8 programs, they're already numbers. But this little conversion step, I have to do it here because I don't have the equivalent of .ls8 files for my computer. So I have to make them right now. So let's get rid of the commas. There we go. And print Beej, I'm just going to look these up over here. Print Beej is 1, and so on. I'm going to convert these. Save register is 3. Print register is 4. And halt is 2. All right. So I've converted my program into numbers here and saved it in a file called program 1. Whoa. There we go. And so now I want to get this thing out of here and load this into it. So memory is just an array, it's just a list. I want to get these values out of this file and I want to load them into this list. So I'm going to take the memory array, I'm just going to nuke it actually. I'm going to make myself 256 zeros. Let me add one more comment here. This is a print Beej instruction, just so we see what's going on. And this is value 10. I guess I better make it match the comment. So I'm going to take this thing and get rid of it. And we're going to write some code to load this list up from this file. So for today, when you're doing your LS8 stuff, you're going to want to unhard code that program that's in there now. There's a print 8 program in there. You're going to want to get rid of that and then write some code like we're going to do right now to load this thing up. So when was the last time y'all did any file I/O? I can't remember when it was. Like file reading and writing. This might be a bit of a refresher. Sprint challenge. Uh, 256 zeros, you can think of it more like 256 bytes of memory. So maybe if I wrote it this way. So here's a binary, 8 bits, that's a byte. Still 0. This whole thing's just 0, right? But I'm making 256 of them. So we'll end up with an array that looks like this, except there are 256 of those, and I don't want to write them all down. Much easier just to write that. So this is just an array, 256 zeros, but can be any number. All right, so this, I'm going to put some comments in here. This is my run the CPU code. And I'm going to add another block up here just to separate it. This is going to be load memory. So I'm going to put some code in here to read this stuff. But I want to be able to run this on the command line like so. I want to be able to run it like that. So me saying, hey, have the computer run program 1. Or if I want to change it, have a different program, run program 2. I can have all kinds of programs. So I need to do some command line parsing to make that happen. I need to see if they specified a program out there. And if we're doing the command line stuff, to refresh your memory, you can get that program name from a list called sys.argv. So the program name to run is argv1. argv0 would be comp.py, argv1 would be program 2 in this example. So let's do a quick test and just make sure that works, because I love testing things to make sure they work before I do anything. So I'm going to print the program name out, just make sure it's working, and then I'm going to exit so that we don't run anything. So let's give it a test. Instruction length. Oh yeah, I put in a bunch of crazy code down here that I need to get rid of. Ignore me for 1 second. Sorry. All right. So this has told me that I can get the name of the file in argv1, which is what I want. And now here's some boilerplate code for reading from that file, a line at a time. So my plan of attack here, let's read a line from the file, let's put it in memory. Let's read another line from the file, put it in memory. And you'll do something very similar today. So with open program name, prog name, I use FP for file pointer. It's my generic name for a file that I have open. Now we just use F. F might be more normal. So you can open a file this way, and then you can do stuff with it. You can read a line at a time using a for loop. So for every line in the file, we can do something with it. Let's print it out just to make sure that our file read stuff is working. So this should open the file, read a line at a time, print a line at a time, which it seems to have done. Scrolled off the screen. It's got blank lines at the end of every one of them. Why do I get double spacing when I print out this file? Anybody know? Why is it printing double spaced? Because print adds a new line. Yeah, the line has a new line at the end of it. So there's already a new line here at the end of this line. I mean, it's not visible, but we know it's there because the thing continues on the next line. So there must be a new line. And then prints a new line by default as well. So that's why we're getting double spacing there. All right, but at least we're reading a line at a time. But we're reading strings in, right? We've got a whole string that looks like this. I want the number 1 out of that. I mean, can I just make that happen? Let's give it a test. Can I get the number 1 out of this line? No. Invalid literal for int. So it doesn't like a lot of stuff. It doesn't like that hash mark. What about spaces? Maybe will spaces be okay? Oh, all right. Spaces are okay. But if you put anything else in there, then no, it pukes. So I need to convert this to an integer because I want numbers inside my computer. But what should I do? How can I get rid of these comments on the line? We could use a regex to do it. What else? Actually, a lot of ways to do this. Iterate through the string, remove any characters that are not numbers. Yeah. We could use like a replace, like a string replace. We could slice it. We could slice the thing. We don't know how many digits the thing is necessarily yet, but because like 10 is 2 digits. If we find a hash mark, we can get rid of the rest of the line. These are all great. No, this is totally it. So what I'm getting at here is there are like 8 zillion ways to get rid of that stuff, and some of them are better than others for different reasons. And you should look at them all and use your judgment. Be like, hey, how do I want to get rid of this? 10,000 ways I could do it. What do we want to do? I'm going to use split. I'm going to use split to make this happen. So split has the backwards one. I can't remember. Oh, better stringify that. Do a little test. Nope, it isn't the backwards one. One of these is backwards in Python. I always forget which one it is. Dot split on a hash mark. There we go. So I can use this to extract different parts of that thing. And then I'll just look at the 0th one. That should be the first part. Join is backwards. All right. And yes, we also need to ignore blank lines. Way to think like a villain. What can I do? Like, this is nicely formed right here, but what can I do to mess this up, right? A villain would be like, oh, you want that, blank lines? How about this? How about this stuff? There we go. Now can you parse it? That's what a villain would do. But let's start easy. All right, so I'm going to take this line. I'm going to split it. Line.split on hash, and then we just want the 0th one. All right. That'll give us the thing before the hash, and then I should be able to get a value out of it, like this. Let's try printing that and seeing if that works. 1 3 10 2 4 2 2. All right. So now I have an integer value that's there. And I know from my experiments before, we can put in leading and trailing space and still get the same result. So that's good. But if I put in a blank line, I think I probably have trouble. Oh, invalid literal for int with base 10, just a blank new line. Oh. What do we got going on here? So let's have a look. Blank new line. So new line is bad. We don't like new line. Otherwise, because that didn't split right. So yeah, we could ignore it. There's also a thing called is it trim on a string? No. Blast. What is it? I've forgotten. Python trim white space. Strip. All right. So the strip method takes white space off a string. So that'll take it off either end. All right. So let's get rid of white space, including that new line. Oops. Now let's see what happens. Invalid literal for int with base 10, empty line. All right, maybe we'll just special case that out there. If line is empty, continue. So jump. If we stripped all that stuff out and the line is empty, let's just jump back up here. Now what do we got? 1, 3, 10, 2, 4, 2. Woo! All right. Let's see. Does this work with a comment? Hell, that was a typo. Hello. Although maybe the typo made sense. Holy cow. So this process that is happening right now, this is really common when you're trying to harden some code against problems. So what happened? All right, we stripped the line and it stripped to hello. That wasn't blank, so we didn't continue. Then we split it, and then we had an empty thing, and then it puked. All right, why don't we move this up here? Let's split it first. And then let's move the strip afterwards. All right, now we'll split it. Then we'll strip the first thing. Then if it's blank, we continue. Now what do we got? All right, great. So things that you should look for. Are there weird spaces anywhere? Do comments exist on lines by themselves? Are there blank lines? And there are lots of different ways to do this. This is just one of them. Okay, but it seems like now at this point, I'm pulling in the numbers. I'm getting them. I'm printing them on the screen. But I don't want to print them on the screen. I just want to store them in memory. And once they're stored in memory, then I should be able to run the program. So instead of just printing them, I'm going to put them in memory somewhere. And I need some index. So I'm just going to call that address. And I'm going to store the value there. I'm going to start address off at 0, where we start loading the program. And then we'll just add 1 every single time we put a value in there. So address is just a little pointer that points along. Now, I'm using the word address because in assembly parlance, this low level, we often refer to the index into memory as the address. So if we're talking low level stuff on a computer with memory, these words all mean the same thing. Index into memory, or index into the memory array, as we have it here, or the memory list. That means the same thing as address. That means the same thing as location, and that means the same thing as pointer. So all these words mean the same thing. They all represent the index into your memory list. The index where some data is stored. And if you go into the world of C programming and get into pointers in C, it means the exact same thing. A C pointer is exactly this. Just in case you go there. So start the address at 0, read the file a line at a time, think like a villain, all the different ways people could mess up your source code here. And like one thing I haven't handled is a case like this. That's going to explode. So it depends on how robust I want to make it. But this level of robustness is enough for the programs you'll get this week. All right. So I've loaded this stuff into memory, and now I just got to run the CPU. What's this supposed to do? It's supposed to print Beej, then print 10, right? All right. Hey, check it out. All right. So I have one of your big goals today is to unhard code the machine code that's in the LS8. Do the same thing. You're going to do something slightly different because in the LS8, if you look at those .ls8 files, the numbers are in binary. They're not in decimal. So when you do this, you're going to need to specify a base in here. I'm base 10, but for you, it's going to be binary. It's going to be base 2. So remember that when you're doing your parsing today. Your numbers in those .ls8 files are base 2 numbers. All right. Think like a villain. What else can I do when I'm running this program to break it? What cases have I not accounted for? What if they add a non-number? Yeah, so I can promise you that none of the ls8 files will have anything like this in it. So you don't have to worry about it. Although you could if you wanted to make your stuff more robust. But now I'm thinking about how many different ways can I run this? What happens if I put in a program that doesn't exist? That's kind of ugly. I'm going to leave that for now, but we could catch that exception and deal with it, make it print something nicer. What else could I do on the command line to mess it up? Bad information. Yeah, I could put like a program name that doesn't exist. I could do Daniel typing. Yeah, like what about this case? What if we specify multiple things? What if I specify 0 things? That's ugly. So the one thing I'm going to do here, and again, you can do this as much as you want to make your code as robust as you want, but at the very least, we should probably make sure we have enough arguments. So what I'm going to do is I'm going to say if the length of argv is not 2, this means the users type either 0 or more than 1 argument. I'm going to print out some usage. comp.py file name. So just a little helper thing right here that tells you how to use the program. So if I come up here and try to run it, sys.argv, oh, sorry, sys. See, I was programming in C last night, mess everything up. Now it tells me, oh, hey, this is how you use it. Better give it a file name. All right, so I'll give it a file name. That's an ugly thing. I can fix that later. But if I give it a file name prog1, it should work. If I give it multiple things, it should tell me, hey, that's not how this works. So that'll make it a little bit better. Now for me, personally, this is where the ls8 comes alive. Just take all my weirdnesses out of there. Should still be the same program though. I can take my program 1 right here. I'm going to paste it into program 2, and we can change this thing around. It's a halt right here. Might as well make that clear. And now I've got another program. And so now I can run program 1, or I can run program 2. suddenly this is starting to feel like a real interpreter in much the same way that Python, when I say Python, the command line, I can run different Python programs. The LS8 becomes capable of running its own programs. And the Beej machine here isn't that capable right now. So I'm kind of limited in what I can do. It looks like I can print some numbers or print out Beej a lot. But that's really kind of it. But as you add more and more instructions, like I said, by the end of the week, we'll have enough instructions in there that the machine will be Turing complete. Then you can start writing actual algorithms in it. Could we have a REPL for the LS8? Yes. Yes, we could. And I have never done that. That'd be an interesting stretch goal. Put it into REPL mode and then just type in. You got to decide what you're going to type in. Are you just going to type in numbers? And then it figures out what to do based on that. It's a little bit weird. Because the REPL executes everything immediately, right? It's like you type a thing, it just executes it. And it doesn't really have much sense of, oh, hey, you want to loop back or call a function multiple times. When you start getting into that world, you get out of the REPL and just write your code in a file, just like we've done with the LS8. But there's nothing really stopping you, I don't think. A lot of real CPUs have a debug mode where they single step through instructions and break every instruction, or sorry, I shouldn't say break every instruction, but interrupt at every instruction so that you can use a debugger. And it would be probably something similar to that. Yeah, you just use input, read in a number, and then decide what to do with that. Or it's probably going to be multiple numbers, right? Because each instruction can be multiple bytes. So you can have a REPL where you typed in something like this to add two registers together, and it would do that result and maybe print out what the register values are or something. Be a fun little project. So for today, we want to do this stuff. This README is out of sync with the other README, so that would have been a good question to ask. But we want to do these things just like we did on the Beej machine here. Unhard code the machine code and put a load function in there to load the program from memory or from disk into memory. And then you're also going to add a multiply instruction. And then you'll be able to run mult8.ls8. It should print 72 when it's done running. I want to point out something in the code here that you saw yesterday inside the CPU class. There's this thing right here, the ALU. I mentioned this yesterday. This is the arithmetic logic unit. This is a big chunk of circuitry that's responsible for doing math. And it's also responsible for doing comparisons between the values in two registers. So the ALU does math stuff, does arithmetic. So if you want to take your code and make it more accurately represent how a CPU works structurally, then whenever you get a mathematical operation, like an add instruction or a multiply instruction like you'll be doing today, you can call into the ALU to make that happen. There's an example here of how this works. The ALU's got 3 inputs. It's got 2 register numbers, register 1, register 4, and then it's got an operation, what we're going to do. Are we going to add register 1 to register 4? Are we going to multiply register 1 by register 4? And so here's an example. If the operation is add, then let's add register B onto register A right here. So calling into the ALU from your main loop will more accurately reflects the structure of an actual CPU. But yeah, remember ALU is good for arithmetic. Finally, in the README here, we got unhard code machine code. So that's what we just did in the Beej machine. Implement multiply and print the result. So this is the mult.ls8 program that you're going to run. Notice it's got a comment on a line by itself. It's also got a blank line in it. So you got to handle those when you read this program in. This is all base 2, so remember to pass base 2 to your int conversion when you convert the string to a number. But if we look at what this program does, it calls LDI, it calls multiply, it calls print, and halt. But if you got to MVP yesterday, you've already got LDI implemented, you've already got print implemented, print number, and you've already got halt implemented. So really the only new instruction that comes into play today is the multiply instruction. And looking at the code, makes sense that it would print 72, right? Register 0 is assigned 8, register 1 is assigned 9. We multiply the two of them together, 8 times 9. We store the result in register 0. So register 0 becomes 72, and we print it out, and then we're done. This last thing right here, didn't talk about this deliberately in lecture today. This is something for you to dig into and figure out. But in here, I've got this ugly loop that's just got if, else, if, else, if, else, if, else. If you think about it, this is an order n operation to find the instruction. When Python is going through this, it's like, oh, is it this one? No. Is it this one? No. Is it this one? No. Oh, it's halt. Okay, finally got it. So it has to go through every if-else block to find the instruction. That's a little bit inefficient, plus it's kind of ugly. So this step right here shows you how to use something called a branch table or a dispatch table to go to functions based on the opcode itself. So basically you're going to have a dictionary. You're going to take the opcode, the instruction value, you're going to look it up in the dictionary, and then you're going to jump to a handler that takes care of it for you. So there's an example here, and you can make use of that example to get rid of that huge if-else cascade. Let's see, would I store the branch table in here or in a separate file? Is that the question? So the branch table is something that exists in Python world. So when the CPU first gets constructed, you can set up a branch table right there. And then branch table for add might be handle add, and branch table for LDI would be handle LDI. And then in those handlers, you can pass in arguments just like this. So the idea is if the current instruction is op1, then you just call this. And if it's op2, then you can call this. So you can set up a branch table where you call every handler and pass in the registers or whatever the arguments were to the handlers. But hack on that a little bit when you get to it, and then ask a lot of questions about it in the help channel, and we can straighten it out, because branch tables are kind of weird when you first look at them, but they're actually really cool and fast, right? Doing a lookup into a dictionary is order 1, so no more having the program scan through every if else to find the instruction. You just look it up in order 1 time and then jump to the handler. All right, that's all I got, guys. You're getting there. I'm getting this thing in place where it can run arbitrary programs. It's pretty slick. Kind of an amazing how much you can get done in such a short time when it comes to writing a program that runs programs. So have fun hacking on it and keep the questions coming. I have one more bonus thing to talk about, but it's lunchtime, so if you got to split. This is only going to take a second, though. It's about compilers. So just like Python runs programs that you pass into it, your LS8 emulator will run programs that you pass into it. But the LS8 programs are pretty ugly, right? They're, where are my examples? The LS8 programs look like this. Just all these ones and zeros. That's pretty horrible. I mean, in Python, we wouldn't want to write this stuff with ones and zeros. We write it in Python. If you want to learn more about how programs take high-level language and convert it into lower-level language or into different languages, that's done using something called a compiler. Python has a little compiler built into it. And I have an example of a compiler that I can share with you. That I wrote a while back. This is a again, this is out of scope, so this is bonus information if you want it. If you don't, go ahead and split to lunch. This is totally extra. You don't have to know this at all for the sprint challenge. I want to be totally clear. But if you want to look at how compilers work, this is a compiler I wrote that compiles from a language called PL0 into JavaScript. And I can show you a little example of PL0 because I have it hard-coded in here. Remember how print 8 was hard-coded near LS8? I never got this far enough to unhard-code the source. So, but I should change this so that it reads this out of a file and then compiles it, right? But this is my input currently. So this highlighted part, this is a PL0 program. PL0 is a simple programming language that was designed specifically for people to learn how to make compilers. PL0 is a simple language. Got some variables up here. Here's a procedure, which is like a function to square a number. So multiplies x by itself and stores the result in square. And then this is main down here. So we have a while loop that prints out basically this. Oh, this is print, by the way. Print out square right there. So this will print out the squares of the numbers between 1 and 10. So that's what this program does. But the question was how to take that and convert it into something else. And that's what the compiler does. It splits it into tokens with the tokenizer. It takes those tokens, passes them to the parser, which turns that into something called an abstract syntax tree. And it takes the abstract syntax tree and passes it to an emitter, which takes that tree and produces the output. And so this is a JavaScript emitter. So this program converts this into JavaScript, and then you could run it. But I could write an emitter for C too. So if you're really curious about how compilers work, this is about as simple as it gets. It's still kind of crazy. Just understanding how an abstract syntax tree works is kind of crazy, but neat. So check it out if you're interested. If you're not, it's not part of the curriculum, so no worries. All right, gang, that's all I got. Anything else before we call it a lunch?
Nope. Thank you very much.
All right. Have fun coding today, and hopefully, I think the first day tends to be the hardest because you're like, how do I wrap my head around all this crazy stuff? But over the course of the week, you slowly get the lay of the land, and you're like, okay, now I want to add more instructions. Not that big of a deal. I've already added 10. I'm adding the 11th. I've got the pattern down. That's how it's going to be at work too. First day, you're going to be like, what is any of this? After a week, you'll start to have it down a little bit. And it takes most people about 3 months at a job before you start feeling like you're in the flow of it. So go compiler written and go. Compilers are called self-hosting when they can compile themselves. It's a landmark for writing a compiler. Usually you write the compiler in a different language because your language doesn't exist yet. There are no compilers for it. But eventually eventually you get your language up to the point where you can rewrite the compiler in your language, and then it can compile itself. It's pretty nuts. All right, let's do lunch. Keep the questions coming on the help channel, everybody. We're watching there, and so ask early and often, and we'll see you out there. Have fun.